Hello, everyone, and welcome to today's Open Fabric Alliance webinar, Coding to Libfabric. A couple of housekeeping things before we get started. This webinar is being recorded, and both the recording and the webinar slides will be made available on the OFA website later. We do encourage you to share the webinar with colleagues who may not have been able to join. And time permitting, there will be a Q&A at the end of today's webinar. So if you have a question, please submit that via the chat feature. Now I'd like to take a moment to introduce our presenter today. Alexia Ingerson Alexia, if you want to go ahead and advance the slides, they can see
Oh
your
yeah, I can do that.
bio there too. Yeah. Alexia is a senior software engineer at Intel, and a maintainer of Libfabric, working on HPC and AI software stacks, including MPIs and CCLs. She's primarily focuses on optimized intranode communication, including leveraging accelerators and use of local offloads and collectives. Alexia, thank you for joining us to present today.
Yeah, thank you so much for having me. Okay, so let's get started. So if you're at this talk, you're probably already pretty familiar with Libfabric and what its goal is, but I'll just give a quick overview just in case so that we all start on the same page. So Libfabric is an open source fabric software library designed to provide low latency interfaces to fabric hardware by exposing communication services to applications through a single API. So essentially, it's a single networking interface that can work on a variety of hardware, each with its own interface and API. So this means that as long as your application is coded to use the OFI interface, it can target systems with any combination of CPUs, GPUs, or NICs without requiring any changes on your side. So say you have a system with Intel CPUs, NVIDIA NICs, and AMD GPUs, no problem at all. Or maybe you're targeting Verb's hardware in the end, but you need to be able to develop your application on a system without verbs and maybe only raw TCP, well, no applications changes needed on your side. OFI will simply just switch providers based on what's available on your current system that you're running on. So this is why a wide variety of applications have added implementations that are coded to the OFI interface. So to name a few up there, MPIs, SHMEM, DEOS, and CCLs. In general, Libfabric can be divided into the API itself and then its providers, each of which implements the Libfabric API, but targets a specific fabric or NIC API. Each provider will use the capabilities and benefits of its specific hardware to implement the requested features through the Libfabric API. There are many examples of limitations and implementation decisions on the provider level, but I won't be touching much on provider-specific architecture. This presentation will focus on the Libfabric API, how to code to that API, and what considerations to make when building your application. The Libfabric API can be grouped into 4 sets of resources and functions. The first is control APIs there on the left, which are used for discovery of capabilities and providers. Second, you have communication APIs, which are used to set up communication between peers. So in a connected-oriented protocol, this refers to the listen, connect, accept flow. And if you're using a connectionless protocol, you're going to be using an address vector, or more simply, just a table of peers referenced by index number. Completion APIs are used to report operation completion. So these can be connection management events like a connected or shutdown event, which will be reported to an event queue, or they can be data transfer completions, which will indicate that data has been sent or received. And those can be reported to a traditional queue or a lightweight counter, depending on your application use. Data transfer APIs are the last group, and those are used for posting outgoing and incoming data or incoming buffers for sending and receiving data. There are various types of these data transfers, including simple messaging, tag matching, RMA, which is remote memory access, atomics, and then collectives. But note that not all providers support all types of messaging. So this is one of those considerations that you should make in your application. So if you rely on a capability that some providers do not support, you're not going to be able to run your application on that hardware. So that limits your use case. Some apps have optimized paths for uncommon capabilities, but most have a default path that uses a bare minimum to make sure that they support any provider. So that's what this presentation is going to cover. What are all these API components and what decisions you can make in your own application that will match your specific use case. So hopefully after this presentation, you'll have a better idea of what your Libfabric API should look like. Okay, before getting into the OFI resources themselves, let's go over the first API that you're going to go through. So this is the call apps are going to use to query Libfabric for usable providers, given the provided parameters and then system interfaces that are available. The application is going to pass in the following parameters. So the first is the OFI API version that the application is coding to. The second is the node name or IP address, which will be a string. Then the service or port number in a string, and those two are optional for address resolution. Then any input flags. So the most common one here is called FI source, which indicates that the node name and port number refer to the calling process. So that's going to be source information. If you don't provide that flag, OFI is going to assume that the node and service refer to a target peer. And then OFI is going to attempt to resolve that node and service. So it's important for OFI to know whether to set the source or destination address on output. Hints are the most important part of this call. They include all the information about the application and what it requires and supports in order to decide which providers are candidates for the app. And I'll go more into depth on that on the next slide. And then lastly, the output from this call is going to be a linked list of all providers that match the application's request and are supported on the system. OFI does its best to return providers in order of which one will probably be more performant. While you can rely on OFI ordering providers for you and then just blindly select the first one, most apps add custom configuration either on build time or run time to make sure that they're selecting the desired provider, which is especially important on non-homogeneous clusters where different nodes may have different configurations. So since every process on every node must call FI-GetInfo independently of each other, it's important for you and your users to know what the target hardware is and make sure to filter the infos appropriately. This can be done by either manually walking through the list and then selecting one by name, or by using the environment variable FI provider, which will make Libfabric only query providers matching that name. A quick note about environment variables in general, though, I try to discourage widespread reliance on environment variables because not only does this create a better out-of-box experience for your users and makes your program more portable, but it can also help avoid issues stemming from multiple layers of the stack using OFI, which has become an issue as a lot of middlewares have decided to use OFI as their transport. So for example, let's say your stack is using both MPI and CCL, and you want to use TCP for MPI and verbs for CCL. Well, setting the FI provider variable is going to cause issues for you. Most settings can be accessed through the API, whether it's querying or filtering it in your infos on GetInfo, or we have this GetOpt call to manually turn settings on or off. So use those whenever you can to make sure you don't mess something up for another layer of your stack. For the FI provider variable, this isn't as important since probably both layers want to use the best NIC on the system, and it isn't an issue for both to do so, but it's just something to be aware of and make sure to consider in your application stack to know whether your application is going to get called in parallel with another communication library, and then make any adjustments as necessary. There's no limit to the number of times you can call FI-GetInfo, though, of course, the more that you call it, the more time your startup will take. So a common behavior that we see in apps is to call GetInfo once with null hints, which will return all available providers on that system and then what they support or require. So this allows the app to select a more performant provider with potentially limited functionality, and then you can call it again with the specific features that you actually decide to enable or use. Okay, before we move on, I want to touch a bit more on this hints parameter because this is key in using the Libfabric API correctly. I'm not going to go too in depth though, because there's a lot of things that you can set here. Each one of those structs has separate attributes. If you want to know more about these settings, I encourage you to look at the man pages for more information. But the two most common terms you'll see in the info, and this goes for the main info as well as those attribute structs, are the terms caps and modes. So I just want to clarify what those two mean. So caps, which is short for capabilities, are features that the applications require from the provider. So if a provider does not support one of the requested capabilities, it will not be included in the returned list. And modes are essentially the opposite. So modes are settings that the provider requires from the application. So in order to return the best provider for your app, it's crucial that you support the modes required for your targeted providers. If a provider requires a mode not set by your application, it will not be included in your info list. So to use the most performant provider, it's important to set not only the capabilities, or to set only the capabilities you require, while also making sure to support the modes that are required by your targeted provider. Okay, let's get into these Libfabric resources that we might be using. So not all of these are required. The ones that are required are outlined in red. The others are going to be dependent on features that you decide to implement or what providers you plan on supporting. Let's start with the fabric. The fabric is the first resource you will be creating, and you can't do anything without a fabric. A fabric represents a collection of hardware and software resources that access a single physical or virtual network. So all network ports on a system that can communicate with each other through their attached networks all belong to the same fabric. All other Libfabric resources will be allocated within the space of that fabric. Passive endpoints are allocated directly under our fabric. They're only required when using a connected-oriented protocol. So a passive endpoint is where we're going to be listening for incoming connection requests and then accept those connection requests. Events associated with connection management will be reported to an event queue, also allocated under our fabric. Then under that is our domain, which defines the boundary for associating resources. So this can include memory regions that are registered for use in data transfers, address vectors, which are used for reliable and unreliable datagram protocols for address mapping, and then completion structures, such as completion counters and queues. Active endpoints at the bottom there are also allocated under the domain, and they are the gateway to your communication. So all data transfers are going to be initiated on an endpoint, and that endpoint can be connected or connectionless. That endpoint also must be bound to at least one completion queue, and if using a connectionless protocol, to an address vector as well. So let's take a look at each one of these resources and the APIs that use them. And let's first just break it up into sections to simplify. So the first is our fabric resources. The fabric itself is created using the FI fabric call. And then the passive endpoint or listening endpoint is created after the fabric using the passive EP call and then passing in the fabric. Similarly, an event queue is created by using EQ open and passing in the fabric. And then that passive endpoint must be bound to an event queue using the PEP bind call. All events occurring on this passive endpoint, like connection requests or rejects, etc., will be reported to the event queue to which it's bound. Okay, moving down past the fabric, our next resource is the domain. This one is created with the call FI domain, passing in the fabric to which it belongs. As I mentioned before, the domain is essentially the boundary for all your other OFI resources. So pretty much everything else is going to be created under the domain. We'll create our address vector, or AV, with AV open, which will be responsible for mapping NIC addresses to an index for simple lookup of peer information. Once again, only required for connectionless protocols. Completion queues are created with a CQ open call. Completion queues are required for all types of endpoints, and an endpoint cannot enable transfers without knowing where to report, send, and receive completions to. Counters also track completions, but are not required. Those are opened with counter open. You can use counters if you don't require knowing information about which operation completed, but rather just want to know how many operations completed. Even if you use counters, you're still required to have a send and receive completion queue for any operations that would require a queue. Memory regions used in transfer operations are registered with the domain using the FIMR-reg family of calls. There are 3 different registration calls here, which essentially all do the same thing, but they'll pass in more or less information about the region. For simplicity and maintainability, I would recommend going through the highest level, which is FIMR-reg adder, ATTR, which is required if you're using more complex registrations, like if you're using GPU memory. And most providers map to that call underneath anyway, so you're just skipping a few steps. Our endpoint, which again is our gateway to all our data transfers, is created with FI endpoint, also passing in the domain. The endpoint starts in a disabled state and then must be enabled after all the required resources have been bound to that endpoint. To bind a resource to your endpoint, use the EP bind call. This call can be used to bind any resource to the endpoint, including counters, queues, and address vectors. An endpoint cannot be bound to multiple resources of the same type. And so by type, I mean both the actual type of resource, so counter, address vector, or queue, but also combined with which flag or type of operation that they track. So you can have a send counter and a receive counter and a write counter and a send queue and a receive queue, and that's totally fine, but you can't have 2 send queues or 2 receive counters. Once all your resources are set up and bound to your endpoint, you can enable your endpoint using the FI enable call, which will put your endpoint in a state ready to send and receive messages. There are 2 general categories of data transfer interfaces. The first are send and receive interfaces, which are 2-sided transfers. So what I mean by this is that not only does the sender have to specify which memory buffer to send, but the receiver must specify where to place that incoming message. So the sender doesn't know where the data will end up on the target and requires that the receiver post a receive buffer for placing that incoming data. So both sides here are involved in the entire data transfer. There are 2 types of send-receive operations, regular message transfers and then tagged messages, which allow for matching incoming messages to posted receive buffers based on a tag, which is helpful for grouping types of messages or directing general category of messages to certain buffers. The other type is remote memory access, or RMA transfers, which are, on the other hand, one-sided, meaning that the sender does not need involvement from the peer side in order to fully transfer the data. So to do this, the sender has to provide a unique access key that it identifies a specific memory region. So the sender here knows exactly where the message is going to go, and the target peer is not involved in specifying the location of the incoming data. Because of the one-sided nature, it's important to note that the target peer will also not get a completion entry for RMA operations since the entire transfer is happening without its knowledge or interference. In order to know when an expected RMA has arrived, the sender can issue a regular send to the target. Once the receiver gets the completion for that send, then it can be sure that the data transferred through the RMA call has arrived. But be aware that the order of these messages is subject to the message order specification, which is in your hence. So you'll provide that. So you have to make sure you provide the correct message ordering if you require it. You use the term RMA to refer to generic remote memory access transfers, but there's also a set of transfers that involve remote memory access, but perform an additional atomic operation on the data. So like regular RMA operations, these are initiated by one side, passing in the memory region key, and they require no interaction from the target side. But unlike regular RMA operations, the data is not just going to be a simple read or write, but a read or write that modifies the contents of the target buffer based on a provided memory operation and data type. So for example, a sum on an unsigned 32-bit value. There's a long list of supported atomic operations and data types, which you can find in the man pages if you want to check it out. The general groups for these operations are regular atomics, fetch atomics, which return the data before the atomic operation occurred, and then compare atomics, which conditionally do an operation based on a condition of the compared values. Like regular RMA operations, atomics do not generate a target side completion event. Which kind of data transfers you request in your app and which ones you use depend on what you're trying to accomplish in your application, as well as what providers you're trying to support and what limitations they may have. One of these provider restrictions and limitations is around memory registration. Memory registration is required for all RMA operations, and then also some non-RMA calls depending on your provider. In essence, memory registration is basically just notifying the domain of any memory buffers that you intend to use in data transfers, and then you give it all the required information about those memory regions that the provider may need. The registrations of these regions is done with the FIMR-Reg family of calls. And during registration, the provider will allocate a descriptor, which is used for local memory, and then a remote memory access key, which is used for RMA operations. So here you can see it passing in those fields to an example, an FI write call. The RMA key is always required for RMA operations, but the local descriptor is only required for some providers. Those provider requirements are specified in the domain MR modes. So when and how to do memory registration is determined by the provider through these MR mode bits that are returned in the FI info after you query a provider. Remember that modes, as opposed to capabilities, are requirements that the provider is imposing on your application. So when querying for providers in Get Info, you must set any MR modes that you can support. If a provider requires a memory registration mode that you do not support, that provider will not be returned in your list. So it's very important for your application to support any modes required by the providers that you plan on targeting. The more modes you support, the more providers your application will be able to support. And then a provider will unset any modes it doesn't need in your application. And then your application is responsible for adhering to the requirements returned by that provider. So here are some of the more common MR modes that you should consider in supporting, some of the ones that a lot of providers require. The first is MR local, which requires registration of any local buffers used. So this includes all local send, receive, write, and read buffers. The registration information for the local buffers are passed into each transfer call using that descriptor parameter. MR raw requires the application to support keys larger than 64 bits. So when this bit is set, apps have to use this MR raw adder call locally to query the key and key size, and then use the MR map raw call at the target peer before using that memory in a data transfer. MR vert adder requires that the application use virtual addresses for the target memory in RMA calls instead of the default zero-based offsets. MR allocated requires that all buffers be backed by physical pages at the time of registration, and those physical pages must not change until the region is deregistered. MR Pro key requires that the MR key is chosen by the provider and not the application. So if you're using this mode, the provider supports setting the key. So if you're not using this mode, the provider supports setting the key through the MR registration attributes. But if you support this mode, it basically means that your application has to support a key exchange between the initiator and target before using an RMA call. MR endpoint requires that the application associate memory regions with an endpoint, not a domain. So after registering the region, the application must bind memory regions to any endpoint which will be using that region. And then lastly, MR HMEM, which requires registration of any buffers allocated using a GPU interface, which in OFI we refer to as HMEM, which is heterogeneous memory. The registration call for these regions will include additional information specifying which GPU API allocated the memory and also which device it's on. Those aren't all the MR modes that we define in OFI, just a few of the more common ones that you might come across. But to find more information on all the MR modes and then how to use them, check out the man pages. Okay, so when setting up your application architecture, one of the first things you need to do is select a connection management protocol, which is done by selecting your endpoint type. To set what type of endpoint you want to use, you can request the type on GetInfo in your hints using the type field in the endpoint attributes. There are 3 different types of endpoints in OFI, and they fall somewhere on the spectrum where you have whether you're connected or connectionless on one axis, and then whether you're reliable or unreliable on the other axis. So those 3 types of endpoints are EP message, EP datagram, and EP RDM. EP message and EP datagram you might be more familiar with because of their non-OFI version. So EP message is basically the same flow as your typical TCP socket. So you first have to create a passive endpoint to listen on a specific port, and then you connect to that passive endpoint. And then at that point, your passive endpoint can accept or reject that connection request. And that accept call will create an active endpoint that is connected to that peer and that peer alone. The comparable OFI calls for this connection protocol are clearly mapped to the sockets interfaces you're familiar with. So just adding that FI prefix at the beginning. So FI listen, FI connect, FI accept, and FI reject. And then data transmission on an EP message endpoint will be reliable, so it is guaranteed to arrive. Now, EP datagram is what you could compare to a UDP socket. So you can bypass the whole connection process and have a single point endpoint send to and receive from multiple sockets. But the downside of this protocol is that your data will be unreliable and your packets might not arrive. So OFI blends the simplicity of a datagram endpoint with the reliability of the message endpoint into a 3rd type of endpoint, which we call EPRDM, which stands for reliable datagram. So this endpoint type is connectionless, but also reliable. Because of the flexibility and reliability, this is the type of endpoint that we see most applications using today. In both connectionless protocols, so RDM and datagram, the app doesn't have to manually connect all the endpoint pairs, so you won't be using those calls on the left, but it will have to insert addresses into that AV or address vector. Since not all providers use the same addressing format, OFI has to map each provider's internal addressing to a universal generic 0-based offset for easy array indexing. So the application has to insert any peer that it wants to communicate with into an AV, and the provider will return the FI adder assigned to that peer. The insertions to the AV are guaranteed to start at 0 and will increment in order logically from what the application inserts. So if you insert 5 peers, your return to FI adders for those 5 peers would be 0, 1, 2, 3, and 4. So you can see from an application point of view how useful this type of endpoint is. Note that not all hardware intrinsically supports OFI RDM protocol. So OFI has internal layering that will provide you with built-in mapping to an RDM protocol if you request it. So it can handle the connection management and multiplexing for you if your hardware is connection oriented. And it can also handle segmentation, reassembly, and retransmission if it's unreliable and you need it to be reliable. So it's very versatile regardless of your targeted hardware. So to zoom in a bit on these different setups, just to clarify, here's what your app might look like if you were trying to communicate with 2 different peers. So in a connected oriented setup, you would have 2 different endpoints, each one connected to a different peer. So if you wanted to send something to peer 0, you would have to initiate the transfer on the endpoint connected to peer 0. And if you wanted to send to peer 1, you would have to post the send on peer 1. You cannot send to peer 1 using the top endpoint, and you cannot send to peer 0 using the bottom endpoint. In contrast, a connectionless endpoint would have a single endpoint that can send to both peers. So which peer it's sending to is indicated by an FI adder that is passed in by the app, and that will map to the internal peer. Okay, so let's go over a quick overview of some of those parameters that go into a typical data transmission call. Each API set has like 5 or 6 calls that you can do, which all do just slightly different useful subsets of the same things. And each one has an equivalent MSG call, which takes in a respective message struct to call the API with more fine-tuned parameters. The message APIs can do everything the other APIs can do. So I'm just going to be focusing on the MSG examples here for simplicity. So for the regular FI message API, your message struct is going to look like this. So the other APIs have the same fields and then just some extra ones for those use cases, but they all have these common fields. The message IOV is just an array of IOVX, each with an address and length in bytes. So these are going to be the data buffers you will be sending out or receiving data into. Note that you cannot touch these data buffers until the message gets sent. So that would be when you get a completion for the transfer. The desk field is going to be an array of descriptors returned from the memory registration calls that I went over earlier. These descriptors give the provider extra information about the sender-receive buffers, and those are only required if the provider sets an MR mode requiring that you pass that in. The IOV count is the number of IOVs in message IOV and the number of descriptors. So this issue comes up from time to time, so I'll clarify. Each element in the desk array refers to the respective address in the message IOV array. So if all your addresses in your message IOV fall within the same allocation or memory region, you can't just pass in one descriptor, unfortunately. You have to pass in an array of that many elements, each one set to the same descriptor for the same memory region. The address here is the peer to send to. So this is the field that will let a connectionless endpoint know which peer in the AV to send to. That one's not used for connected endpoints since the endpoint is inherently connected to only one other peer. The context is just a pointer to track the operation. So that'll be returned in the completion queue entry so you can quickly identify which operation completed. But you don't have to pass one in unless the provider requires it. If it does, your info mode will be set to FI context or FI context 2, which will indicate that the provider needs to point to either 32 or 64 bytes that it can use internally for tracking the operation. So that one doesn't mean that you can't use the context for other purposes, just that the first field that it points to has to be an FI context that the provider can use, which can be followed with whatever application fields that you need for tracking. And then lastly, this data field is optional data that you can send with your message, which will be available in the remote CQ entry. To send this data, you either need to use one of the APIs that specifically sends data, or you can use this message call and set the flag field to include the FI remote CQ data flag. Often people use this field to send the global rank or address index for easy identification on the remote side of which peer this message is from, since source addressing is not always available and then sometimes has overhead to get. So those are the pretty widely used fields across the data transfer APIs. So I want to take a look at an example of what these would look like in the flow with a completion queue. Okay, so here's an app, and for our purposes, we're going to have a single CQ, which is tracking our sends and receives and our receives. And then we're also going to have two counters, but those are separate. So one counter will be tracking receives and one will be tracking our sends. Since I just want to illustrate the updates to our CQ encounters and what the general flow is here, we're going to consolidate our send and receive sides and just send to ourselves. So the send and receives are going to be reported to the same CQ. So you can do this in your application, but right now you're probably mostly thinking of your app handling remote sends and remote receives. So in your use case, the completions would actually come in two different CQs, one on the send side and one on the target peer. Again, this example is just for simplicity. So the first step in our flow is going to be to post receive. So for our use case, we're going to specify a single buffer, which is 128 bytes long, and then pass in the descriptor associated with that allocation. The source address here can either be an FI adder if you want that buffer to only receive messages from a specific peer, or it can be set to adder unspec, which will receive a message from any peer. The FI adder field is only valid if you request the directed receive capability. Otherwise, it will always be treated as an adder unspec. And then the last field is that context parameter I was talking about to track the operation. Next, we issue our send, which will initiate our transfer of data from txbuf into rxbuf. And this transfer will only be 16 bytes, so it's not going to need all 128 bytes of the receive, but it is going to consume the entire posted receive. There is a capability that lets you receive multiple smaller messages into a single posted larger buffer. That's called FI multi-receive, but again, that's an extra feature that we're not using here in the example. So for this example, it's just going to be a 1-to-1 ratio of sent message to receive buffer. The send will be specifying the descriptor if needed and the destination address for the message, and then that context for the send operation as well. Okay, once that message has been sent and received, we're going to be getting 2 completion entries into the CQ. The order of these will depend on your provider and what settings you're using, so it won't necessarily be in this order, but you will be having 2 entries. So here we see that one got inserted, and then we also can see that our receive counter got incremented. So right away, we can get a glimpse of what that completion might be for. A completion entry can have the following fields: the context parameter it was sent with, flags that tell us what kind of operation completed, the length of the message, the pointer to the receive buffer, which is only available with that multi-receive flag. And that'll tell you where within that large buffer this message is. But for regular receives, it's not set, since it's just going to assume that it's at the beginning of the buffer. The optional remote CQ data if the sender sent some, and then the tag if you're using a tagged call. So let's see what's in this completion. Okay, so this one has the context set to RxCTX. So that's the context we posted our receive with. And then the flags have FI receive. So that tells us that a receive completed, and then the length is 16. So even though our whole buffer was 128 bytes, we didn't need all of them. And that's perfectly fine and normal. So this field lets us know how many of those bytes were actually used. The rest of the fields are nothing, since we didn't use that multi-receive flag to tell us the buffer. We didn't send any CQ data, and we're also not using the tagged interface, so those are not going to be valid. If they were valid, say like the message had CQ data that we can read, or it was sent with the tag, that information would be communicated with the flag set accordingly. Then we should get another entry, and this time we see our send counter got incremented. So that's going to be our send. Our send completion is going to have that context set to txCTX, which we used in the send call. The flag is going to be set to FI send, and then the rest is actually going to be invalid. So half of these fields are only used on the receive side, since on the send side, we know what buffer we sent and how much data we sent, and the CQ data is for the remote side as well. So if you do need any of that information in the completion entry processing on the send side, then you should probably be using that context parameter to track it yourself. Now you can see that for our use case, we don't need all of the completion fields. So it feels a bit silly to always save space for all these fields. So you can optimize some of them out if you don't need them. And this is done on CQ creation when you specify the CQ format. So here you see the different formats. So tagged is your most verbose option with all the fields available. Data omits the tag. Message only gives you the context flags and length. And then your lightest option is context, which will just return the context. Okay, there are a few more things that I want to mention when talking about completions. The first one I already referenced, but it's that order of the completions is not actually set in stone. So the receiver doesn't always, the receive doesn't always come in before the send completion does. The send completion could get written into the CQ before the message has arrived, or even before it's been sent, which I know is confusing. So when the application for a send gets written is subject to the completion semantics that you specify in your app. If you don't specify, the provider is only guaranteed to provide the lowest level, which is called inject complete. So inject complete only guarantees that you're able to reuse the send buffer with no impact to the send. So the data might be on the wire, or it might have just been copied into an internal provider buffer. If you want to make sure that the data is actually being sent to your peer, you can use the next level up, which is transmit complete. Transmit complete guarantees that your data has been sent, meaning that you could basically close your connection down and the data would still arrive. So this level is commonly used at the end of an app's life before closing to make sure that we can close down properly without leaving the peer hanging. Transmit complete only guarantees that your data has left your side, but not that it's arrived at the peer. So if you want to know when the data has actually arrived, you need to use the highest level of completion, which is called delivery complete. So delivery complete ensures that your data has arrived at the destination and also has been processed. Note that this doesn't necessarily mean that it has made it into the intended location, though. So if the message arrived, but the peer has nowhere to put that message, the sender can still complete that send correctly with delivery complete semantics. Be careful with higher completion semantics, though, since adding higher semantics, mostly delivery complete, might force the provider to have to send acknowledgments to let the sender know when data has arrived, and other extra round trips. So the higher the completion semantics you use, the more of a performance impact you might see. Now, I mentioned that delivery complete ensures that it has arrived, but not that it's necessarily in the right spot. And that leads me into another consideration, which is around unexpected messaging. Unexpected messages are what we call incoming messages that don't have a matching receive. So basically don't have anywhere to go. So in the example I showed, we posted the receive first and then the send. So the incoming message could be placed in that receive buffer immediately when it came in. But if we'd done it the other way around, so we issued the send first and then processed that incoming send, we would have nowhere to put it because there was no posted receive from the application. So that would have been an unexpected message. An unexpected message isn't really unexpected. It's just early. The receive is coming. It just hasn't happened yet. The implementation on how to handle unexpected messages is provider specific, but it often requires some internal buffering, and so it usually comes with an extra copy. So it's important to build your application taking this into consideration. So can you anticipate where to put messages? It's hard to avoid unexpected messages completely in these large-scale applications where load balancing is difficult to perfect. So some peers are going to finish earlier than others, which might lead to some missing receives. But I recommend thinking about the architecture of your application to consider how to minimize these unexpected messages when possible to help with performance and memory consumption. And then the last consideration I want to touch on is regarding when completions get generated at all. By default, all but one set of APIs are going to be generating completions in your queue, with the exception being the inject family of calls. There's one or two of these calls in every group of API calls, and these don't generate a completion and also guarantee that your buffer is free to reuse immediately after calling the inject call. So basically, they have an implied immediate completion with inject complete semantics. Those are generally used for small messages that can fit into a packet payload and where an extra mem copy is pretty trivial. The use of those calls is subject to the provider inject size limitation, which is returned in your FI info. While the inject doesn't generate a CQ completion, it will still increment the send counter if you are using one. And then the other way you might be able to suppress completions is by using a capability called selective completion, which, like the name suggests, allows you to select specifically which calls to generate completions for. So it will turn off the default completions, and then you can choose which ones you do want a completion for by using the FI completion flag in your send. This one is often used with counters, so it removes the overhead of having to populate and copy all those completion fields for all the entries and lets you use those lightweight counters if you just care about how many operations completed and not necessarily which ones. So which of these tools to leverage or take into account is dependent on your use case. So I'm not going to tell you what to do. That's totally up to you. Okay, I want to take a minute and touch on what I think is kind of a confusing topic in OFI, and that one has to do with the idea of running progress. It's especially confusing because we updated it recently for some performance implications regarding threading and locking, and it's pretty easy to use poorly, so I want to go over these changes. So in your info domain attributes, you have a few different progress fields. There used to be just one progress, which referred to your data progress, because control progress was inherently thread safe. So it can be split up into two fields now: a control progress and data progress. But we kept the generic progress field for backwards API compatibility. I'm not going to really explain why it works that way, but I'll tell you what you can and should do now if you're using the newer API. So you can set your progress fields and your hints to what level of progress you support. There are 3 different settings for this progress field. The first one is progress auto, and it basically pushes responsibility of driving progress to your provider. So when I refer to driving progress, I mean calling either a CQ read call or reading a counter. So both of those calls should look to the hardware and see if there's anything to do, and then write entries on the queue and update the counter if necessary. Note that while the provider might be driving progress automatically, it's still your responsibility as an application to eventually read any entries off the CQ. Otherwise, you're going to run out of memory. Not all providers support auto progress because it often requires a provider thread to drive this, and it can introduce extra locking as well. So if you require this, you might be limiting your provider use case and also causing some background performance issues. The second progress setting is manual progress, which means that you as an application are responsible for periodically calling a progress function to yield time to the provider to process incoming or outgoing messages. So since you as an app know when there should be data coming in or going out, you should be better equipped to know when progress is needed. So it can have better core utilization. So what this requires you to do is periodically call into CQ read, which can be as simple as an FI CQ read call on your CQ with null entries. So you don't necessarily have to read any entries off your CQ. You just need to yield time to the provider. This is often required if one of your send or receive calls returns E again, which indicates that the provider needs progress to be driven for the call to succeed. The last type of progress is the new one we added, which is called Progress Control Unified. And what this requires is that you as the app need to drive progress. So it basically means manual progress, but it also unifies the data and control paths. So basically that all your data and control calls are under the same threading model. And this is the confusing part because the issue was that the control interfaces were originally written to be inherently thread safe. So the control interfaces include basically anything with the fabric or domain, so your connection calls as well as AV inserts or registration calls, which was an issue because if your provider has to guarantee built-in serialization of to your domain, but then you're using domain resources on your data progress path, then your path has really coarse locking, which defeats the purpose of your threads if they all have to lock left and right. So I know that's really confusing, but essentially what I want to emphasize here is that number one, not all providers support auto progress and it requires more locking. And then because of that, so I suggest you use this new progress model and then drive progress manually while also not assuming control operations are thread safe. And then you can reduce most locking on your data paths. On that note, I just want to go over some of our threading models. Since you can have a lot of bottlenecks on resources if you don't use them properly, it's important to organize your resources in the correct way. So the first model is the one that pushes all serialization control to the provider. And this one we call thread safe. So say you have 2 threads and they're both trying to send to the same endpoint. And then read from the same CQ and do control operations on the same domain. So if you are not controlling those access calls on your application, you're going to need to request thread safe to make the provider basically lock everything. So once again, you have pretty coarse locking here, and there's not a lot of benefit from the threads, at least from an OFI perspective, but maybe your threads are using most of their cycles doing non-OFI computation, so maybe it's trivial to you. Again, this just depends on your application. But if you had something like this set up, and need OFI to ensure thread safety for everything, you would request this model in your HENS. So FI thread safe. Now you could make it better by maybe dedicating an EP for each thread. So it would look something like this. So now you have two endpoints under the same domain, and each thread uses its own endpoint. So you eliminate the bottlenecking on the EP calls like FI send, but that's actually pretty much it. This used to be called thread endpoint. So it meant that you had a thread per endpoint and controlled all endpoint calls on the app side. But the truth is that it wasn't that helpful because every send call would require CQ recalls to progress them anyway and read entries from the CQ. And that actually didn't really help with the CQ bottlenecking, so we deprecated it. So if you do use something like this, you would still need to request thread safe to have the provider serialize all your resource accesses. In order to get rid of those CQ bottlenecks, you would need to dedicate a thread per CQ. So this one we call thread completion. So basically meaning that you have one thread per completion device, and the app will manage serialization to each CQ. A lot of applications started using this model, and this definitely helps. But the problem is that sends and receives on those endpoints are using shared domain resources. So they're using the same AV, the same memory regions that are registered, everything. So if they need to look up information in the domain, there is still locking that needs to happen to control access to those resources. So again, it's better, but you still have a lot of bottlenecking on the data path because of the domain. So let's separate the domain to get rid of those. So now you have two domains and all your thread resources are completely separate. So this removes practically all locking on the OFI side, which is ideal from a communication standpoint. So we've been trying to move threaded applications to our thread domain model, which means that the application is going to have a thread per entire domain and serialize access within that domain. There's a memory and startup drawbacks here though. So obviously you have twice the number of resources that you have to manage in your application. That's not too hard to do. But the other thing to consider here when using this model is regarding memory registration. So ask yourself, are both endpoints going to be using the same memory? If they're not, then that's easy. You can just register the memory on the domain you're using and then manage it per domain. But it might get tricky if you're using the same memory on both threads, because now you have to register it on both domains. So each region has two MRs and descriptors for OFI, one for each thread. And then it gets even more complicated if you think about RMA keys. So what do you do if the same region gets registered twice, but with two different keys? And if those keys are provider keys, you have to exchange both keys with the peer. So definitely a lot of considerations with this model, because it does push all of the responsibility to your application to handle these cases. So it all depends on what you want to do and what you're willing to do. If your application, like I said, is compute heavy and only periodically goes to the network, then maybe it's not that big of an issue for you. But if you're going to be reliant on the network, then my recommendation is to separate these as much as possible and architect your application to handle those considerations. Okay, that was a lot. Hopefully I didn't lose you. So this is all going to be recorded and the slides will be available, so don't worry about absorbing everything. But here are the general things I want you to take away today so that you can get started on your application. Okay, so the first is always ask yourself, what hardware are you targeting or do you want to support? Is there a limitation or optimization for that hardware? If there is, make sure to support that use case or be able to leverage it somehow in an optimized path if it's available so that you can maximize your performance. Second, keep your required capabilities as simple as possible to maximize your provider usage. So don't write an application that absolutely requires a random capability that only one provider supports. You're really going to limit your application. Maybe you have an optimized path that can leverage that if it's available. Well, great, sure, but don't always require it. Third, try to support as many modes as possible to maximize your provider usage. Some providers have things that you need to support them, so if you support more of them, you can use more providers. And some providers don't require modes, but have optimizations that you can enable if you do support something. So you can leverage more optimizations as well. And then, of course, if the provider tells you to do it, then make sure you're actually doing it. It's helpful to call GetInfo with null hints, which will often return a provider's most optimized sets of capabilities and modes. So you can look at those and make some decisions and trade-offs for your specific use case for what you actually want to request and enable. And then lastly, if you're using threading, I recommend, if possible, to use thread domain and progress control unified, which is basically manual progress with control serialization, and that will pretty much remove all the locks on the OFI side. There are so many tools and optimizations you can leverage in OFI. That's the great thing, and also the overwhelming thing about Libfabric, that you can really fine-tune your application with all these hardware capabilities and use cases. But it also means there's a lot of considerations to make when writing your application. The good news is that the whole point of OFI is to try to provide a reasonable out-of-box experience and try to make the best decisions for you so you don't have to. So you can always just do the bare minimum in your application, and it will probably be not too bad, and then you can build it from there if you do need more. Okay, well, that's all I had. I hope you get some insight into what's going on in OFI and feel ready to tackle your application. So with that, I take some questions, I guess. Let me pivot over to this questions. I'll stop sharing also. All right, let's take a look. Okay, so Q says, there doesn't seem to be a way for an application to tear down a domain, tell the provider we're done and to free resources. Would it be useful for long-lived programs and debugging programs? Am I missing something? This can be done. To tear down a domain, tell the provider we're done. I mean, is it possible to unmute to clarify some things? I don't know if that's just, I don't know if there is. My clarification question for that just would be that we do have a call that does tear down the domain. If things are still going on it, then it'll return ebusy. So are you referring to either just a way to notify like, hey, close down when you're done, or are you saying some sort of fallback for that ebusy? Theoretically, when you close your domain, if it returns ebusy, you could try again. Once that's free, let me see. So, or the provider level shut down name server thread. It's a good question with the name server thread. That should just happen when you when your application exits. So a lot of so like the fabric will get closed and might either shut down your name server thread for you, or just whatever last application is using that thread will shut it down. But when we have a lot of things that are initialized on Fabric initialization, so when your application starts up, it should, you know, start these services and things. I think it depends on your provider. I think that the provider, at least that I'm thinking of, starts the name server thread on GetInfo, I believe. So your first GetInfo call would be creating that thread, and then whenever your Libfabric call exits, it will be cleaning that thread. So not exactly, but in terms of your domain and the endpoint that you're shutting down and things like that, they're all the FI close calls, which would be tearing down the FID. Let me know if I didn't answer that. I'll keep going on questions, and then I can clarify if you have another one. Oh, you're the next question. Great. Node and service args to GetInfo are not very clear. Can either or both be other formats than TCP IP address and port number? For example, FI adder strings. Should we be using them going forward? Okay, great question. So The problem here is that a lot of providers have proprietary addressing. So not all of them have a standard way to represent them in a string like IP addressing. So the node and service are intended to be the IP addresses, which is why it works with TCP or verbs, which because it uses the RDM and ACM. So those IP addresses do work, but it actually breaks with other providers that don't have that string representation. So they are not required. I generally don't use them. I generally just leave them blank. And then once you create your endpoint, it'll assign that the name for that specific endpoint on that RDM. So basically, my recommendation, don't include the node and service args. And then once you create your endpoint, let your provider set an address internally, and then you can do an out-of-band exchange to exchange all those addresses and then insert them in bulk. The node and service kind of it lets you select your node and service, your port, but it is restrictive to say the least. Okay, thanks, Hugh. Answered. FI insert is a single transfer at a time type of function. Is there an equivalent batch function insert efficient enough that a batch version of the function doesn't provide much benefit? Yeah, great question. I'm assuming you're talking about AV insert, hopefully. AV insert takes in an AV, a list of addresses, and then the number of addresses in that list. And then the return, it can be an array. So it will insert, if you pass in 10 at once, it'll return all those 10 all at once based on your count parameter, and then set that array of 10 addresses all at once in that single call. Hopefully that was what you're asking. All right. Sweet questions. I love them. Especially that node service one. I get it a lot, and I was going to add stuff on that if we had time. So thank you for asking that. Awesome. Thanks, Doug. Cool. So that's all I had, and it's the top of the hour. So I think we'll call it there, Matt.
Good. Thank you, Alexa, for your presentation.
Yeah, absolutely.
Just a reminder that the webinar has been recorded, and both the recording of the webinar and the slides are going to be available on the OFA site later. So again, on behalf of the Open Fabric Alliance, thank you all for your time and for attending today's webinar. Have a good day.